arrivata una richiesta di consenso per caso per la registrazione? Ok,
no,
sembra che
è partita da sola.
Ah, vabbè, sembra che sia partita adesso, vabbè. Allora, veniamo a noi. Per cambiare le slide mi muovo da questo lato io. Okay. Allora, oggi, come vedete, iniziamo il modulo 2. È un modulo, se volete, un po' teorico, un po' formale, però che mi serve per introdurre poi il formalismo che useremo quando poi cominceremo a mettere realmente le mani nella fisica. Mettiamo Federico. Ok, stiamo iniziando adesso. Quindi, vabbè, allora, diciamo, la prima parte di quello che vi mostrerò oggi è qualcosa che trovate in tutti quanti i testi di meccanica quantistica non relativistica o in testi di teoria dello scattering. È qualcosa che immagino, non so a che livello di profondità l'avete anche già fatto l'anno scorso nel corso di ENISA almeno. Quindi non vado nel dettaglio e allo stesso modo non pretendo da voi il dettaglio su questo per l'esame. L'importante è che riuscite a seguire, diciamo, la discussione che ci porterà innanzitutto a formulare la famosa regola d'oro di Fermi, okay? Sulla quale poi si basano le sezioni d'urto e i reti del decadimento. Allora, direi di partire così. No, non così. Allora, per andare... Ah, devo fare... Ah, forse conviene che faccia cosa. Faccio cambiare la pagina. Devo fare così per forza. Vabbè, facciamo così. Okay, so now I switch to English. So, as you know, particle physics deals with two essentially types of processes, which are collisions and particle decays. And in both cases, one has to calculate the transition probabilities between the initial and the final quantum states. Now, let's consider a physical state, which is described at the time t is smaller than t0 by this wave function here. So this is the initial state wave function, psi I, okay? Where phi I is the eigenfunction of the unperturbed Hamiltonian. Is a stationary state, essentially, okay? And so it corresponds to an energy eigenvalue EI. So this is the eigenvalue equation for the unperturbed Hamiltonian. There is no potential, there is nothing, just for a free particle. So this is the eigenfunction, this is the eigenvalue. And the eigenfunction, since there is no any kind of interaction, it is, of course, a plane wave. Okay. Now, suppose now that at a certain time, t equal to 0, an interaction potential starts to be effective. Now, of course, the total Hamiltonian becomes the sum of the unperturbed Hamiltonian and an interaction term, that is a potential energy term, that we can call EV for simplicity, and which is related to the potential U through a coupling constant that we call for the moment G0, and that can be anything, depends on the potential. So in the case of the electromagnetic interaction, for instance, this coupling constant is just the electric charge of the electron, okay? So this depends, of course, on the kind of interaction. So we say very general here. Now, so at the time t greater than t0, where now the potential is effective or has been already acted on the state, the wave function of the system must satisfy the time-dependent Schrödinger equation that you find here with the total Hamiltonian here, right? And the solution of this time-dependent Schrödinger equation, okay, must be expressed as a superposition of all possible final states. Okay, so we run the index A from 1 to n, supposing that we have n possible final states, originating from the interaction of the system with this potential. And this coefficient here, which depends on time, so this time-dependent CKT coefficient, represents the probability amplitude to find the system in a given final state phi k. Okay. Now, clearly, at the time before t0, so before the potential is acting, okay, the probability amplitude for the initial state must be 1, and the probability amplitude for any possible final state must be 0, okay, for any final state. This is before the interaction. After the interaction, of course, this is not anymore the case. However, as you probably know from quantum mechanics, in perturbation theory, it is assumed that the potential U is sufficiently weak that it can be treated as a small perturbation. And as a consequence, the transition probabilities are very small for the final state, are very small at any time. So still, at any time greater than t0, the probability amplitude for the initial state is still almost 1. And the probability amplitude for any final state is very small than 1, although it is not 0. Okay. This is because, you know, in perturbation theory, any potential is treated as a very small perturbation. So the effect on the system is very minor. Now, let's consider the wave function for one possible final state. Let's call f or psi f, okay, which is given in the usual form. And then one can construct the so-called transition probability amplitude, that is this matrix element. We have the initial state here, the final state here, and your potential energy in between. And this you can write in the bracket formalism, or if you prefer, in the integral formalism. Of course, the two are absolutely equivalent. And now it turns out that we will not show this, but okay, you can take this from textbooks if you want. It turns out that the probability amplitude CF to find the system in the final state psi f is just the Fourier transform of this transition probability amplitude. So we can calculate the probability amplitude for any specific final state f as the Fourier transform of the transition probability amplitude TFI. The next step is to introduce the so-called transition probability rate. So considering now all possible final state, one can define the total transition probability per unit time, or the so-called transition probability rate, which is defined this way. So the W is 1 over T, this is because we have a rate here, okay? And then it is the sum of all the probabilities to find the system in each single possible final state. So this is a discrete sum. Okay, we are summing from 1 to n, where n are the possible final states. But now we can switch from a sum to an integral here. Okay, and the reason is the following: in most collisions and decays, the final state particle can actually occupy any energetic level among all those possible allowed by simply requiring energy conservation. So the sum over all possible discrete quantum states, this sum here, can be replaced by an integral over all possible energies in the final state. Now we can replace our expression for the probability amplitude Ck for the final state, which is the Fourier transform that we showed before. And so we end up with this quite complicated expression, where we have a double integral, and this Fourier transform comes squared inside the integral. And also let me call rho EF, this ratio here, the n over the f, that is the number of final state per unit final state energy. We will go, of course, more in detail for this. So once we solve these two integrals, okay, and this we will not show in this course, but you probably found in some advanced quantum mechanics books, but I don't care. You end up with the famous Fermi golden rule that you probably have seen already in the last year courses, which is a constant. Then we have the transition probability amplitude squared, okay? And then we have this density of final states, rho E, that is the n over the EF, and which actually describes the number of final states available per unit interval of energy. So this is a quite crucial result that was already derived by Fermi 1 century ago, and which is at the basis, as we will see, of the calculation of any cross-section for collisions or decays. Okay. So what we have here, we have two main ingredients, two main components for the transition probability rate. The first component is the transition probability amplitude, TFI, which include, of course, the potential. So which includes all the dynamics of the process. Okay, all the physics of the process is contained here. And then the density of final states only accounts for the phase space available in the final state. So it only accounts for the kinematics of the process. So here we have the dynamic of the process, and here we have the kinematic of the process. Altogether, they contribute to the transition probability rate. Now, as we have seen at first order in perturbation theory, the transition probability amplitude is just this one, okay? But then we can, of course, make a power expansion, so we can go to higher order. And at second order, we have a sum of two contributions. The first one is this one, so is the standard scattering in a potential. And the second term, okay, which is this one, represents the transition occurring through some intermediate state K, you see here. Okay, and then of course one can go to third, fourth, and so on terms. However, since we're working in perturbation theory, so since the potential is a small perturbation, clearly all the higher order contributions are smaller and smaller and smaller. So in principle, one can already obtain a sufficiently accurate prediction already, taking into account only the first lowest orders. Okay. So leading order, next leading order, or next leading order, or probably is already enough. Okay. Now, so we obtained, without real proof, but the expression of the Fermi-Konden rule. Let's now derive the expression of this kinematic term, which is the density of final states. So we are here. Let's consider, suppose we have a reaction or a decay, okay? Let's consider a final state particle, okay, that can occupy some spatial volume, VSP, SP stands for spatial volume, and which turns out to be in this momentum interval. So from PF, F stands for final state, of course, so PF to PF plus dPF. Now we can represent this interval in the momentum space, okay? So if you go in the momentum space, this interval corresponds to the volume of this spherical shell here that you see, okay? Where the inner radius is exactly PF, okay, this one, and the thickness of this shell is dPF, okay? So in the momentum space, here we have, let's say, Px, Py, Pz, okay, momentum space, the final state particle will occupy this volume here, which is nothing else than the volume of a spherical shell. So the surface of the sphere times the thickness of the shell. So it's 4 pi Pf squared times dPf. So we now have the spatial volume in the final state and the momentum volume in the final state. And of course, altogether, they provide the total volume in the phase space. Phase space is a generalized space that consists of both coordinates and spatial coordinates and momentum coordinates, as you know. Now, according to the uncertainty principle in non-relativistic quantum mechanics, each particle occupies a volume, so an elementary volume in the phase space, which is given by the Planck constant to the third power, or if you like, the h bar times 2 pi to the cube. Okay. So this is the phase space volume occupied by one single particle, and this is instead the okay, we will see in a moment. So now we have all the ingredients to calculate the density of final states. So this is dN over dF. Okay, this we simply put outside. Now we have to express correctly the number of particles in this infinitesimal phase space volume. And this is given by, of course, the total infinitesimal volume available in the final state, that is the spatial volume times this spherical shell in the momentum space, divided by the phase space volume occupied by one single particle. So the ratio of the two gives you the number of particles. Total volume divided by the volume for one single particle in phase space, of course. So now we just substitute. So this remains V, Sp. And now here we put the full expression of the momentum of the volume in the momentum space, 4 pi Pf squared dP. Then we have the elementary momentum in the phase space for one single particle, and then we still have this dEf. Now, very straightforwardly, we will derive this expression using classical relation. So this dP over dF turns out to be just 1 over V. V is the velocity. This you can obtain with the simple arguments. just using classical relations. Okay, so this is the momentum, this is the kinetic energy. You take you differentiate the momentum of the energy and take the direction, you just end up with 1 over v. Okay, so this is for the moment the expression of our density of final state, where for the moment I mean that we are neglecting for the moment the spin of particles, and this we will consider later on. Now, no, sorry. So finally, we found this expression for the density of final state. Okay, let me make 2 comments here. First of all, this one in the note. So the density of final state increases quadratically with the momentum of the particle in final state. Okay, and so final state with lighter particles, which are produced, of course, with a larger momentum, are kinematically favored over final state with heavier particles. Okay. This is quite obvious. If you produce at the same amount of energy, the center of mass, you produce lighter particles in the collision or in the decay, those particles will share, of course, a larger momentum. And so the phase space will be larger, and so the transition probability rate will be larger. If, on the other hand, you consider a final state channel with only heavy particles, these heavy particles will be, of course, slower, so they will have a much lower momentum. This depends quadratically, so the phase space will be much, much smaller, and as a consequence, also the transition probability rate. Let me also put your attention here on this volume term here. So this I single out for the moment in this place, but we will see in a few slides that this is actually not relevant. Okay, and I will show now in a moment. So, and this is all about wave function normalization. So, to ensure a correct volume integration for the probability amplitude TFI, the initial and final state wave function have to be properly normalized. So let me put here a normalization coefficient, A here and A there. Oh, sorry. So, as you probably know already from quantum mechanics, actually from non-relativistic quantum mechanics, each wave function is typically normalized to 1 particle in a cubic volume of side L. That means that the normalization is such that one has a probability 1 to find a particle inside a cubic box of side L. Okay, you see here. And of course, then this means that the wave function has to satisfy some boundary conditions. So the wave function of x plus L, y, z must be equal to the standard one. The same is for x, y plus L and z, and the same is for x, y, z, x plus L, and all the other combinations, of course. So this is the way wave functions are typically normalized in non-relativistic quantum mechanics. And the consequence is the following. So if one now imposes the probability density normalization, so psi squared, normalizing the total volume of this box, okay, you impose that this is 1. This is the way the normalization, of course, is defined. Then you end up from the integral, you end up with the square of the normalization coefficient coming from here, and the total volume of the cube coming from this integral over the spatial coordinates. And this has to be 1 by definition. And so you can now extract the square of your normalization coefficient, which is 1 over L cubed. That means 1 over the spatial volume, right? And so you can also take the square root of this. So your normalization coefficient here and there is just 1 over square root of the spatial volume. Okay, so this is a standard result in quantum mechanics, non-relativistic quantum mechanics. Now, this is an important point because, of course, the calculation of the transition probability rate must not depend on the normalization volume. Okay, this is just a convention, so we cannot. The final results cannot depend on the convention. And in fact, it turns out that the volume dependency, the expression of the density of final state, so this VP dependence that we have seen before. Let me go back here. This VP dependence here. Okay, cancel completely with the inverse of VSP factor, which is associated with the proper wave function normalization that appears in the square of the transition matrix element TFI. Okay, so when you consider the full Fermi golden rule, where we have both ingredients, the rho and the square of TFI, these two volumes will cancel each other. Okay, so at the end we don't have essentially any dependence, and so it is convenient to rewrite our density of final state just by setting VSP is equal to one. Okay, so since this is irrelevant at the end, we can put any arbitrary value. So let's put it 1. So it will disappear from this expression here. So this is now the, let's say, the almost final expression of the density of final states that describes the phase space of the kinematic available in the process. There is one more thing to add here. Suppose we have a reaction of this type, A plus B that goes into C plus D, okay? And suppose that the particle in the final state, okay, and also in the initial state, have a non-zero spin. So let's now take into account also the spin of particle. Then, of course, the number of available final states has to be increased by the spin multiplicity factor. Okay, so we have this additional multiplicity that contributes to the number of possible final states if one takes also into account the spin of particles. Okay, and so we can actually add this GF into our final expression of the Fermi golden rule, and so this is the total, the final expression we derived. Okay, so we have the constant here, we have the square of the transition probability amplitude, which contains the physics of the process, so the dynamics of the process, and then we have now the full expression of the density of final states. Okay, which also in this case takes into account the spin multiplicities of the final state particles. L'ho fatto? Non so come l'ho fatto. Ok, chiaro fin qui? Siete riusciti a seguire?
Sì.
Ok. Quindi diciamo, ovviamente ho saltato molti passaggi, ma non mi interessano i passaggi, mi interessa che seguiate la logica di questo discorso e diciamo sempre come si arriva poi a esprimere in modo completo la regola di Fermi. Okay? Bene. Okay, now, all this was derived in a non-relativistic scenario, okay? But clearly, if you now want to generalize this in a relativistic framework that we need for particle physics, we have to change something, okay? And the reason is already quite visible here. So it's the wave function normalization that does not work anymore in relativity. So the wave function normalization of one particle per unit volume is not Lorentz invariant. And the reason is that if you now look, if you are in the boosted frame, so along the direction of motion, the one of the 3 dimensions, so the one parallel to the direction of motion, will be Lorentz contracted by factor of gamma, as we studied last week. So there will be, let's say, a contraction of 1 over gamma. That means mass over energy. So the contraction is, let's say, inversely proportional to the energy of the particle. So in the boosted frame, okay, the special volume is not just L cubed, but is L cubed divided by gamma, which is proportional to L cubed divided by the energy. And so it is not universal. It depends, of course, on your reference frame. So it is not anymore a good way to normalize your wave function when you are in relativity. So thus the original normalization of one particle per unit volume corresponds to a normalization of gamma particle per unit volume in the boosted frame, reference frame. Okay, so it depends on gamma. So in fact, in relativistic quantum mechanics, a different choice is made. So a Lorentz invariant choice of the wave function normalization must be proportional to the energy, must be proportional to E particles per unit volume. So not one particle per unit volume, but E particles per unit volume, such that the increase of energy will compensate the effect of the Lorentz contraction. Okay, so we increase energy in this way, and we have an inverse dependence here, so the two cancel, and overall, this definition of the normalization will be universal, will be constant. Okay, so you cancel this energy with this energy here, and you end up with something which is constant, that you can use as a normalization. Okay. Now, in practice, the convention is not to normalize to E particles per unit volume, but to twice E particles per unit volume. This is the convention, okay? So your normalized wave function in relativistic quantum mechanics will be given this way. The normalization coefficient is square root of 2e. And so now when you take the normalization, when you integrate over the full volume, your normalized wave function, you get 2e, okay? This is the way wave functions are normalized in relativistic quantum mechanics. Sorry. Okay. Having said all this, we can now move on to the definition of the cross-section. So we will apply what we have learned about the Fermi-Golden rule and see how these contribute to the calculation of cross-section of any process. Okay. Okay, so let's consider a fixed target reaction, A plus B that goes into C plus D. We define the flux as the number of incident particles per unit time and per unit area. So VA is the number of beam particles per unit time, seconds, and unit area, square centimeter. Now we can make this trick. We can multiply and divide by centimeter, such that here we now have the number of particles. Sorry, I cannot do this way. So we have the number of particles over a volume. That is the volume density of particle. Okay. And here we have a velocity, the space over second. So overall, we can rewrite the incident flux for beam particle A as the volume density of particles, so the number of particles in the volume, times the velocity of these particles. Okay. Now, it is, of course, intuitive that the number of interactions per unit time, or the interaction rate, okay, between a beam particle of type A and a target particle of type B. So again, this is our reaction, remember? Okay. So this interaction rate, this interaction rate is proportional to the incident flux and also to the total number of target particles in a given volume. The higher the flux, the higher the rate, but also the higher the number of target particles, the higher the collision rate, really. So we have a proportionality here, and this is intuitive. And we can make this as an equality if we now introduce a proper proportionality constant that we call total cross-section. Okay? So the collision rate is equal to the total cross-section of the process multiplied by the incident flux multiplied by the number of target particles in a volume V. Now, the total cross-section, as you already know, has the dimension of a surface, of an area, so square centimeter. And so we can now invert this reaction and find the relation for the total cross-section. So the total cross-section is now, just by inverting this relation, is just the rate, the collision rate, or the decay rate, divided by the number of particles in the target. So, okay, we're talking about the collision here, divided by the incident flux. But if you now look at the numerator is the number of interactions per unit time and per target particle. This is nothing else than our transition probability rate that we defined before. Okay, and the incident flux we get here is NA times BI. So it's the density, the volume density of incident particle times their velocity. Okay. So our cross-section, okay, is in a way proportional to our transition probability. Okay, and this of course makes sense. So in principle, we can now substitute here the full expression of the Fermi-Golden rule that we derived in the previous slide. Okay, let me now switch to the blackboard and do some simple passages. Ok, riuscite a vedere la lavagna e me?
Sì.
Ok. Okay. So we obtain that the total cross-section is the transition probability rate divided by the volume density of the beam particles times the velocity, Vi. And now we can substitute the full expression of the transition probability rate that we obtained through the Fermi-Golden rule. So this is 1 over NA Bi, and we have 2 pi over h bar. Then we have our squared transition amplitude. And then we have our density of final state. Okay, let me now also put here the expression of the density of final state that we derived. So this we can write as 2 pi over h bar. Then we have Fi squared. And then we have the speed multiplicity, gh. And we have 4 pi, the momentum of the final state squared. And we have the volume density of the initial particle, the velocity of the initial particle, the velocity of the final state particles, and then we have the elementary volume in the free space. Okay, so now we can make some very simple passages, and we can write this in a more convenient way. So it's 1 over 2 pi squared h bar to the 4th power. Okay, so we are multiplying this by this. Now we have T Fi squared. Then we have the spin multiplicity factor, the momentum squared, the initial velocity, the final phase velocity, 1 over NA, and then 4 pi at the end. And this 4 pi, as you can already imagine, okay, is the total solid angle. And let's now derive this. Can I clear? Posso cancellare? C'è qualcuno che sta ancora copiando?
Può cancellare.
Ok. Adesso quello che faremo è di motivare, perché questo 4π è proprio l'angolo solido totale. Allora, vediamo una motivazione del genere. Abbiamo, we have a fixed target collision, okay? So we have a beam of particle A, and then we have a fixed target. Okay. So, beam, and then we have a fixed target of particle B, okay? And then after the collision, A plus B, okay, let's consider an infinitesimal volume, okay, which is, of course, so the total volume will be a sphere. Let's consider infinitesimal cone here, where this surface here, dA, is infinitesimal surface, okay, and where this distance here is R. Now, by definition, as you probably know already, the infinitesimal solid angle is given by the infinitesimal surface divided by R squared. This is the definition of the elementary solid angle. Now we can write the infinitesimal volume in polar spherical coordinates. So d tau, which is dx, dy, dz. We can also write as r squared dr sine theta d theta d phi. This is the infinitesimal volume element. And so back to here, our infinitesimal solid angle element is dA over r squared, and this we can write as d tau divided by dr over r squared. Okay, so we obtain a surface by dividing a volume divided by a distance, a length, and so taken here, this simply results in sin theta d theta d phi. And this is the elementary solid angle. Let's now integrate over the full volume. So the sigma dot is just the integral over the omega. That is the integral from 0 to pi of sine theta d theta times the integral from 0 to 2 pi of d phi. So these are elementary integrals. So the first one to be, so the second is just 2 pi, there is nothing to do here. The other one is minus cosine theta from 0 to pi, or 2 pi cosine theta from pi to 0. Let's just substitute here. So this is 2 pi, and then we have cosine of 0 is 1, minus cosine of pi is minus 1. And so overall, we get 4 pi. So now, now we can rewrite our sigma total cross section as 1 over 2 pi squared h bar to the fourth, square the transition amplitude, and then we have gf times Pf squared divided by initial velocity, final velocity, and omega dot. So this is the total cross section, and once we have this, we can simply obtain the differential cross section. So the sigma in the omega, okay, so differential with respect to the solid angle, which is simply 1 over 2 pi squared h bar 4 Pf pi squared Gf Pf squared divided by Bi Bf. Now, in this, so there was, if you remember, originally also a 1 over Na coefficient, okay? So we assume now just for one single particle, Na equal 1, it is a single collision between a big particle and a target particle, okay? And so when we put Na equal 1, this kind of disappears. This is now the expression of the total and differential cross sections. Ok, ci siete?
Siamo?
Ok. Torniamo sulle slide. Come si fa? Così? No. Sì. Allora, vedete le slide adesso?
Sì.
Okay. Okay. So this is what we derived. Okay. So this is the differential cross section for a single incident particle, n equal 1. Okay. And with the scattered particle emitting an infinitesimal solid angle d omega. Now, why is this quantity so important? For two different reasons, depending on your case. Okay. So suppose you measure very well experimentally the differential cross section for some process. Okay. So you have a precise measurement of all these things here. Then you can derive information on the transition amplitude, probability amplitude. Okay. Suppose that you don't know the shape of your potential. If you measure this precisely, you can infer the shape of your potential. So this is a very useful technique when you are dealing with, for instance, a kind of interaction that you don't know how to express, so what kind of potential it is. And this could be, for instance, the case of the QCD, as we will study. Okay, QCD in the large-scale regime, okay, where the theory is non-perturbative. This will be studied at the proper time. There is no way to okay, make prediction on the potential. So you can only make measurement, and so then use the measurement to make prediction on the potential afterwards. The opposite case is when instead you know very well the potential. That is the case of quantum electrodynamics. Okay, so you know precisely the potential, so you can calculate precisely this quantity, and so you can make prediction for the cross-section to be measured experimentally. Okay, and then compare theory with experiment. Now, another note, okay, we have been talking about total cross-section, but in general, the total cross-section is given by the sum of the elastic cross-section and inelastic cross-section. So elastic cross-section is a process, the cross-section of a process where the initial and final state particles are the same, okay? Although they have, of course, a different, each particle has a different momentum. Inelastic is a case in which the final state system is different from the initial one. So it is either in an excited state or is completely different, as we will see when we will study the structure of the proton, for instance. Okay. So in the initial state, for instance, you have an electron that goes into a proton. In the final state, you destroy the proton, and you have a bunch of hadrons that come from the fragmentation of the quarks. This is what we study, of course. But it is a very general relation. Now, the other warning I want to put here is that this expression here, okay, is still based on non-relativistic quantum mechanics, okay? But, you know, we want now to work in a relativistic environment. And so we cannot use this expression because this is not Lorentz invariant. Okay, so it works very well for low energy phenomena where you don't need to use special relativity, but when you go to high energies, high velocities, you have to be relativistic, so this expression then becomes wrong. So we have now to derive the corresponding expression in quantum for a quantum relativistic description of your system. Okay, and let me go here. So let's neglect for the moment again the spin degrees of freedom. Then the Lorentz invariant expression of the total differential cross-section for a generic two-body reaction, E plus B, they go into C plus D, and in natural units, so we put h bar equal 1, that means that h becomes 2 pi, is given by this expression here, okay? So now here, on the denominator, you recognize the normalization, the Lorentz invariant normalization coefficients, okay, for the wave function of particle A and particle B, okay? Here, again, we have a probability transition, okay, but now it is a Lorentz invariant. So this Lorentz invariant transition probability amplitude is related to the previous one, okay, through this coefficient, which properly takes into account the Lorentz invariant normalization of the wave functions, okay. And then these are the velocities, and then so pretty much the same now, and this is now again the density of final states, okay. So again, we have some normalization constant, a transition probability amplitude squared, okay, and then the phase space described in terms of these density of final state. How can we express now the density of final state in a Lorentz invariant way? And this is the way we do this. So we have essentially two terms here corresponding to the two final state particles, particle C and particle D. And then we have this Dirac delta function that ensures four momentum conservation. So these are now four momenta, okay? And this means that the total final state for momenta must be equal to the total initial state for momenta. So this delta here enforces four momentum conservation, okay? These two terms here, okay, actually represent the Lorentz invariant elementary phase space, okay? So we don't have any more 2 pi h bar to the cube, as in non-relativistic quantum mechanics, but instead, okay, the element of Lorentz invariant phase space for one single particle is given by this expression, okay? And if you have n particles, it's the product of n particles, okay? Here you just have two, because it is a two-body reaction, C plus D. Now we can put everything together. And so we obtain now the relativistic invariant expression of the total cross-section, okay? So we put as a factor the normalization terms and the velocity of initial and final state in the central mass. And then we have, of course, the integral over the full phase space, okay, of the squared transition probability amplitude. So the structure is pretty much the same, but now in a Lorentz invariant way. Suppose now that we have a generic reaction where A plus B goes into n final state particles. So we can generalize this to the case of n final state particles. And so instead of having these two final state, elementary final state terms, we have the product of all n of those, okay? And all the rest is the same. So this coefficient here only deals with the initial state particle, the beam particle, and the target particle, okay? So these remain unchanged. And of course, when you enforce the form momentum conservation, you now have the sum of all n final state particles for momentum must be the same as the sum of the initial state for momentum. So this is the way, the most general way to express the total cross-section in relativistic quantum mechanics, so in a Lorentz invariant way. Now, by definition, a Lorentz invariant quantity must be the same in all reference frame, okay? So it remains unchanged under Lorentz transformation. So let's consider again the process A plus B go into C plus D, and let's consider now the differential cross-section in the center of mass frame, where we know from the previous lesson that the center of mass energy, square root of S, is the sum of the energies of the two particles in the center of mass system. So the star here indicates that we are working now in the center of mass system. And in the center of mass system, of course, the three momenta, the total three momenta must be zero, okay? So the initial state momenta and the final state momenta must be zero. And so we can call take the moduli of the initial and final state momenta, PA equal to PB equal to, let's call it PI star for the initial state. And for the final state, PB is equal to PD is equal to PF star. And so we can now write down in the center of mass frame, the general expression of the differential cross-section, okay? So S is the Mandelstam variable, and these are the three momenta in the center of mass for the final state and initial state. And this is the usual squared transition probability amplitude. And then you can integrate these over your solid angle, okay, and obtain the total cross-section. So these are those two rather fundamental expressions that we will be using sometimes also later on during the course. So, of course, take memory of these expressions. Okay. Now, so far we have neglected completely the spins of the particle. So let's now generalize D to the case where also particle have spins. And suppose that we are doing a so-called unpolarized experiment. So we are not measuring the polarization of the initial particle state, but also of the final subparticle state. So if we are not measuring the spin, so we don't know which are the spin state of each particle, we have to average over all possible spin in the initial state, and we have to sum over all possible spin in the final state. So the average is the sum of all possible spin state divided by the total number, which is given by the multiplicity of the spin state in the initial channel. And then you have to sum, we have another sum here on the final state spins, okay? Now, we can write this in a more compact way, okay? And this is the notation, where now this symbol here represents the spin average transition matrix element squared, okay? So this is, again, the full expression of the differential cross-section in the center of mass frame, okay? Where, in the case where we do not measure the spin of the initial and also of the final state particles. So if we do not measure them, we have to average over the spin of the initial particle state and sum over all possible final state spins, okay? So this is our, let's say, averaged squared probability transition probability matrix, okay? Okay, let's, okay, we can even make a 5 minutes break, ok? Facciamo una pausa?
Sì, va bene.
Ok, poi continuiamo con i decadimenti, quindi abbiamo studiato adesso le reazioni, ok? Collision process, e poi ci muoveremo adesso, generalizzeremo anche in modo, diciamo, Lorentz invariant, come trattare correttamente i decadimenti. Va bene, ci fermiamo 5 minuti e facciamo, dai, ci vediamo alle 10:05. un po' più di 5 minuti.
Va bene?
Ok.
Ciao a tutti.
Ciao.
Ciao a tutti.
Ciao ragazzi, qualcuno viene al bar con me?
Vengo io, Bitta.
Ok, top, andiamo.
Andiamo.
Io sono già al bar, vi aspetto lì.
Grande.
Yasso, sei bravo.
Avete chiesto qualcosa, ragazzi? Mi ero allontanato un attimo.
No, stavamo chiacchierando tra di noi, prof.
Ah, vabbè, fate pure, fate pure.
Professore, scusi, volevo chiederle una cosa.
Sì,
Ho notato che sul video precedentemente caricato su YouTube
sì.
si vedeva praticamente la lavagna. Si vede che probabilmente quando fa la registrazione dal suo schermo deve selezionare, quando lavora la lavagna, diciamo, la sua finestra.
Ah, mannaggia. Quindi se non seleziono la finestra qui, la registrazione prende soltanto la slide che è rimasta... Ho capito.
Perché mi sa che registra proprio quello che lei vede sul suo schermo.
Ho capito, benissimo. Credo che oggi l'ho fatto fino adesso, l'ho fatto correttamente, credo. Ci starò attento, ovviamente. Sì, sì, d'accordo.
Ma si figuri, ve l'ho detto soltanto perché potrebbe essere utile, appunto.
No, hai fatto bene a dirmelo, hai fatto benissimo a dirmelo. Sì, adesso il sistema è cambiato, siamo con Google Meet, ma credo che oggi l'ho fatto bene e ci starò attento. Ti ringrazio molto.
Ma si figuri.
Ok, possiamo riprendere?
Sì?
Per me sì.
Ok. Allora. Okay, so we discussed quite in detail how to derive the expression of the cross-section, the differential cross-section, either in non-relativistic quantum mechanics and in relativistic quantum mechanics. So taking properly into account the wave function normalization, and also write down in Lorentz invariant, in a properly Lorentz invariant way, the density of finite states. Now and this was about, let's say, collisions. So E plus B that goes into C plus D. Let's now develop the, let's say, analogous formalism for decays. Okay. Now, the mean life or the decay time, which are essentially the same thing, we call them tau, of an unstable particle. Okay. So it is defined in the center of mass system of the decaying particle when the particle is at rest. Okay. Otherwise, you have to boost it. Okay, as we've seen in the first lesson. So the decay time is a number in seconds or a fraction of seconds that is measured when the particle is at rest. It is, of course, specific of each particle. So different particles have different or even very, very different decay times. Okay? And it corresponds to the time needed to have about 2/3 of the original particle decayed. So this is a very simple concept that you probably already know, but let me just repeat this. So let me move to the... Where are we? Ok, vedete la lavagna?
Sì?
Va bene. Ok, so you know that when you have a decay, you have to use the standard decay exponential law. So the number of particles survived at a certain time t is equal to the initial number of particles, and then this number decreases exponentially, okay, like t divided by tau, minus t over tau, where tau is the determinant within life. Okay? So in the specific case, when t is equal to tau, one has that the number of particles at the time tau is equal to n0 times e to the minus 1. It is n0 divided by e. And this turns out to be 0.37 and 0. Okay, so 1/3 of the total number. And so the number of decayed particles at a time, let's say, t equal tau, is equal to the total number of particles minus those that have survived. I think all these survived, and these also survived. Okay, and so this is n0 times 1 minus 1 over e, that is approximately 2/3 of n0. Okay, so in a time corresponding to in a time interval corresponding to the mean life of the particle, the number of particles that have already decayed is 2/3 approximately of the total number of particles. Vado a tornare alla slide. Ok, vediamo se torna alla slide adesso. Okay. Back to the slide. Now, as I was mentioning before, so the mean life or decay time is specific of any particle and can be very, very different. Okay, so the tau can vary essentially from infinity for stable particles, such as to our present knowledge, the proton or protons or electrons, to something like 900 seconds for the neutron. You know that the neutron is an unstable particle that spontaneously decays into a proton, but can also be very, very short as 10 to the minus 24 seconds, okay, for many hadrons, as we will be studying later on in the course, okay? Now, also for the case of decay, we want to define the transition probability rate, okay? And in this case, it is simply given by the inverse of the mean life, okay? So this is the same W we've seen before for collision processes. Now it's just, in case of decay, it's just the inverse of the decay time. That means that the higher the decay probability transition rate, the smaller the mean life, and of course vice versa. Now, let me come back for the moment again to hadrons. Okay, so hadrons, as we will study, of course, are subject to the strong decays. Okay, and they experimentally, from the experimental point of view, they appear. These decay are studied in terms of resonances. So these hadrons, sorry, appear like resonances in a plot where you have the cross-section as a function of the energy. So suppose you can increase the energy of your accelerator, okay, and you measure the cross-section, you will get some points here. At the end, you get a curve like this, okay? This is a resonance, okay? It's described by a Breit-Wigner function. This will be studied, of course, later on, okay? Let me now just anticipate, okay, that this is the way hadrons appear, okay? And the reason is that their decay time can be so short, if the decay is regulated by strong interaction, that it is unmeasurable experimentally. So there is no way to have a detector so fast that can measure such a short times. So the only thing you can do is to reconstruct the shape of the resonance, okay, and then to calculate the width of the resonance, okay, which is called the decay width, and by definition is given by the full width at half maximum. Okay, so you take the half height, and you take the width at half the height of this resonance. Okay. And now, how is this related to so the decay width is in a very simple way related to the mean time. Okay. So let's consider the uncertainty principle that you know very well from energy and time. So delta E, delta T is equal to h bar by 2. And as, let's say, an uncertainty in energy, we take half of this width here. So half of the full width at half maximum. And as our time, we take the decay time tau. And then we just extract the product of the two. So this is just gamma tau equal h bar. And so we can extract gamma at the end, which is h bar over tau. But then we have seen in the previous slide that by definition, the probability, the transition probability rate is the inverse of the mean life. So we now have a relation that puts everything together. We have the decay width here, the mean life, and the transition probability rate. Okay, so we can make some comment here. So the higher the transition probability rate, so the larger W, of course, the greater the decay width. So the resonance will appear very, very wide if this W is large. And at the same time, the decay time will be very, very, very short. So also of these sides here, okay? 10 to the minus 24, for instance. The decay width, okay, provides a transition probability per unit time for decay process. And so we can call it also the decay rate. Okay, so this is a rate, so this must also be a rate. And in fact, it is 1 over a time. Okay. Therefore, by measuring the decay width, one can infer the decay probability W, And so one can infer, okay, in turn also the shape of the potential, because W contains the potential through the transition probability, the transition amplitude squared. Okay. So suppose you measure, you make very precise measurement of the shape of the resonance. You can very precise measurement the full width of maximum, and this immediately gives you the decay time and also the transition probability, which in turn contains the information of the dynamic of the decay, so of the potential that has regulated this decay, which is of course included into the transition probability inside the W. Okay. Now, the decay width, okay, we introduced in this way by talking about hadrons decaying strongly, so through the strong interaction, but of course is a general concept and can also be used for electromagnetic and for weak decays, as we will see. Okay. Now, when you talk about decays, you have to think that one single particle can decay in different possible ways. Okay, so in general, the particle can have different decay modes. And each decay mode has a different probability, okay, its own probability. And each mode, so, is characterized by the so-called branching ratio. So the branching ratio is the ratio between the partial width for a given decay mode I divided by the total width. So when considering all possible decay modes, okay. And so, of course, by normalization, if you sum all the partial widths, you obtain the total width, and the sum of the ratio will give you 1. Let's make an example. So let's consider now the pi plus. This table I took from the particle data book. I will give you a reference later on. So now this is the mass of the particle. This is the lifetime of the pi plus. That is order of 2.6 10 to the minus 8 seconds. Okay, and these are all possible decay modes of the pi plus. And what you see here is the corresponding branching ratio. Okay. So you see that in 99.99% of the cases, the pi plus decay into a muon and a muon neutrino, okay? But with very, very small probability, it can also decay into other modes, okay? Now, another important point here is that many decay channels may arise from different mechanisms. So suppose, in principle, one can have some decay mode which can be obtained through a strong decay, some decay mode that can be obtained through a weak decay, and some decay mode that can be obtained through an electromagnetic decay. So in general, you can have all of them. Now, for the case of charged pions, pi plus or pi minus, this is not the case. So these objects are as we will study, are the lightest hadrons. So they cannot decay into other hadrons, otherwise they will violate energy conservation. And so the only way they can decay is through the weak decay. And you can also infer this because all of these decays contain a neutrino, okay? And as we have seen in the first lesson, the neutrino can only fill the weak charge, and so can only take part of weak processes, okay? So this is a very specific case, but in general, particle can decay in a strong way, and through the strong interaction, through the weak interaction, or through the electromagnetic interaction. We will study all these, of course. Now, let's now write down the Lorentz invariant differential decay rate, okay? So essentially, we have the same formalism that we already introduced before. So suppose we have now a particle A decaying into n final state particle, okay? Then we have the squared transition amplitude, the normalization coefficient for the wave function of the initial state, the elementary phase space volume per each of the n final state particle, and the delta function that ensures the form momentum conservation between initial and final state. So the structure is exactly the same as the, let's say, differential cross-section, okay? And so now we can integrate these over the phase space and obtain now the decay rate, okay? This is the differential, this is the total, for a decay process like A that goes into C plus D. So this is a particular case where we only have two particles, so n equal 2, and so one is particle C, one is particle D, and you also get this here in the form of momentum conservation there. Now, this is the general expression for any two-body decay, okay? For n body decay, you can, of course, extract from this general expression here. Now, the fundamental physics is contained into the matrix element. So as usual, all the dynamics of the process, okay? So the physics, the kind of potential, so the kind of interaction, this information is always included here, okay, into the matrix element, because it depends on the potential. Whereas all the additional factors here, okay, they just arise from phase space constraint and energy momentum conservation. All right. Let's now close with decays and discuss the last topic of today, okay, which will, let's say, set the fundamentals for the Feynman diagram that we'll be studying in the chapter of quantum electrodynamics, okay? So we will now introduce the formalism and, yes, and the notation that we'll be using later on when we study the fundamental interactions, the quantum electrodynamics and the QCD, and also the weak interaction. So let's start with a very simple situation. So let's consider again a non-relativistic, now we are back to non-relativistic, transition probability amplitude at first order. So as we have seen at the beginning of this lesson, this is the way, okay, to write down the non-relativistic transition probability amplitude at first order, okay? And now we work also in the Born approximation, so we assume that either the initial state and the final state particle are described by plane waves, okay? This is the usual element of volume in polar spherical coordinates. And now we describe our potential energy in terms of the potential and a coupling constant of G0, okay? Much like the way we already discussed before. Now, everything, of course, depends on the shape of our potential, okay? And a particularly interesting interaction potential is this one that you see here. So it's G divided by 4 pi, e to the minus R divided by capital R, all divided by R. Now, this turns out to be a static central potential, okay? Both strength depends only on the distance R that enters here and here, as generated by a point-like source with infinite mass. So suppose we have a very heavy object, that means that we can completely neglect the recoiling of this heavy particle in the scattering process, okay? So we have a heavy particle that we can consider infinitely massive, that generates a central potential in the space. And then there is an incident particle that will interact with this particle through this potential. Now, this capital R denotes the range of the potential, and G, okay, is an integration constant that is proportional to the intensity of the source of the potential, okay? So this is a quite general but very interesting shape for the potential. And let me also note you that if you substitute G over 4 pi, which is a constant, with the electric charge Q, and you let the range of the interaction goes to infinity, so we get rid of this exponential here, then we simply obtain the Coulomb potential, Q over R. Okay, so this potential here is a more general potential, static central potential that, for instance, reduces to the Coulomb potential if you make these simple substitutions. Okay, we know that the range of the Coulomb potential is infinite, and so this exponential term drops, and then if we just call Q this, then we get out this, the Coulomb potential. Now, in particular, okay, if we express R, capital R, in this way, as h bar divided by mc, where m is a mass of a particle, this is the potential originally introduced by Yukawa in 1935. This is also called the Yukawa potential. And Yukawa actually introduced this potential, this you probably already know, in an attempt to describe the internuclear forces in terms of exchange of boson. So already in 1935, Yukawa had a very modern view of how interactions evolve. So two particles actually interact by exchanging some boson, okay? And so he essentially generalized this potential, okay, by relating the range of the potential through the mass of the exchanged boson, okay? And this is the Yukawa potential. So originally he introduced this potential to study the internuclear forces, so the forces that act when two atomic nuclei okay, get close and interact themselves. Now, he also made a very interesting prediction, because now imposing that the range of the nuclear forces is of the order of the size of the atomic nuclei, so order of a few Fermi. So if you put now here a few Fermi and invert these, it found out that the mass of the hypothetical exchanged boson should be of the order of 100 MeV, okay? And this was, in fact, the prediction of the existence of a light boson. Now, the Yukawa particle, so this light boson was in turn discovered in 1947, and it turns out to be exactly the pion, so the pi meson, with a mass of 140 MeV. And this was discovered, as we will study later on, in 1947 by studying cosmic ray showers. However, 1 decade earlier, so in 1936, another particle was discovered, that was the muon, with a mass in the same range, so order of 100 MeV. And so this was originally confused with the pion, so with the exchanged boson in the nuclear interaction. And then it took 10 years approximately to figure out that the muon is a completely different particle, although the masses are quite similar. The muon is a lepton, and it has nothing to do with the nuclear forces. Okay, it is not even a boson; it's a fermion. Now, the pi meson was then, okay, once discovered, so this was a sort of confirmation of the Yukawa theory, the pi meson was considered to be the carrier of the nuclear forces that keeps atomic nucleus bound, or that take part of nuclear collisions, nuclear reactions. Okay, this is of course an old view of how things actually are. Today we know that the pion is not a fundamental particle. Okay, the pion, as we will study, is a bound state of a quark and an antiquark. And that at the fundamental level, now at the very fundamental level, the strong interaction, so in turn also the interaction between nuclei, is mediated by gluons, where gluons are the gauge bosons of the strong interaction, as described by the quantum thermodynamics. Okay, so this is now the modern view, and this will be studied, of course, in a dedicated chapter of this course. Now, let's now derive the transition probability amplitude for the Yukawa potential. So I will switch now again to the blackboard. All right. Okay, so let's start from the transition probability amplitude at first order. So EFI given as phi f of this conjugate, our potential energy, our initial state with function, and we integrate over the volume. So we work in the Born approximation, so we assume that both the initial and final state with function are just plane waves. So this is e to the minus I over h bar, p f scalar r. Then we have our potential. And then we have the initial state function, I over h bar, pi scalar r in the time. Now we write more explicitly the potential energy term as the potential times the coupling constant that we can put outside of the integral, so d0 here, then the integral of u of r, and then we also merge these two exponentials, so it is e over I divided by h bar, and then we have ei minus ef scalar r. These are all three vectors, standard three vectors. This is a non-relativistic treatment, of course. Okay. And then we can define the transverse momentum Q as pi minus f, and so we can. So this is still in detail. And so we can write this down as G0 integral of U R e to the I over H bar Q scalar R in the top. So this is because the free momentum transfer. Okay, initial momentum minus final momentum. Okay, let's now work in natural units. Okay, let me write this here. So in natural units, we know we put H bar equal to 1 for simplicity. So our transition probability amplitude that we can also call as FQ is a function now of the transfer momentum. That is 0 integral of U of R e to I Q star R in the lab. Now we make explicit that we substitute here the Yukawa potential, and we make explicit the volume integration. So this turns out to be G0 G over 4 pi triple integral e to the minus r divided by capital R divided by R. Now we develop here the scalar product, so this is I Q R cosine theta. And then we make explicit also the volume, the volume, so it's R squared dr sine theta d theta d phi. So this is from 0 to infinity, integral over R. This is from 0 to pi, integral over theta. This is from 0 to 2 pi, integral over phi. Let me continue here. So we have G0, G over 4 pi. Now let's make more, let's separate the three integrals. So this is the integral from 0 to 2 pi in the phi. Okay, there is nothing depending on phi, so this we can put already outside. Then we have the integral from 0 to infinity of e minus r over r divided by r. That also includes the integral over theta, 0 to pi, e I q r cos theta, sin theta, d theta, and all these goes s squared dr. Okay. Now the first integral is trivial, it's just 2 pi. So we have 0 g over 4 pi times 2 pi. Then we have integral from 0 to infinity of e to the minus r over r divided by r. And then this is a known integral. So the solution of this integral you can find in textbooks is sine of q r divided by q r, and then you just have r squared in the r. Okay, now we have 2 pi times 2 goes into the 4 pi here. And then we also have r, and r squared that goes away. And so at the end, we have G0, G, integral from 0 infinity e to the minus r over r sine of qr divided by q in dr. So we are left now with the last integral, okay, over the distance r. So we know from the Yukawa theory that capital R is h bar over mc. And so in natural, sorry, let's go here. In natural units, R is just 1 over m. Okay. So we go here, we substitute here, and we also express this quantity in terms of the Euler formula. So this is G0, G, integral from 0 to infinity, e to the minus r m, that comes from here. And then we have the Euler formula, e to the I Q r minus e to the minus I Q r divided by 2 I Q in the end. And then one is just left to solve this integral, okay, which is also a non-integral. Okay, I don't care about the solution, how to solve the integral. I will just give you the result. So the result will be 0, g, and then we have 1 divided by q squared plus m squared. Ok, ci siete tutti?
Sì, sì.
Ok, avete tutti copiato la lavagna?
Fatto?
Sì.
Ok. Allora, torniamo alla slide. Ok. Okay. So this is our result. Okay. So we have expressed our transition probability amplitude, which is a function of the transfer momentum Q. Okay. This way as G0, G, which are the coupling constant and the strength of the potential, divided by Q squared plus M squared. That we can also write as G0, G, and then this capital pi is equal to 1 over Q squared plus M squared. Okay. Now, what is this? Okay. What have we obtained? So this quantity describes the probability amplitude for the scattering of a particle, okay, this one here, which is coupled through a constant G0 to a static potential generated by a point-like source of infinite mass m and intensity g. Okay, so there is nothing really exotic here. Okay, it's just the probability amplitude for the scattering of this particle with this potential, assuming that the potential is generated by a point-like very massive sources. So we are neglecting the recoil of this particle here, and that the incident particle, okay, has a coupling constant is 0, and the intensity of the potential generated by this particle is called g. Okay. Now, what is really new is actually the interpretation of Yukawa of this same quantity here. Okay. So in the Yukawa approach, the quantity pi 1 over q squared plus m squared, okay, so this denominator here essentially, is interpreted as the probability amplitude for the exchange of a boson, okay, of mass m and 3 momentum q between two interacting fermions. So suppose this line represents one fermion, the incident fermion. This line represents the, let's say, the other fermion, so the target fermion if you want, okay? So this quantity here that we calculated, okay, is nothing else in the Yukawa approach than the probability amplitude for the exchange of a boson with mass m and momentum q between these two interacting fermions. Okay, so the boson acts as the mediator of the interaction between the two fermions, and this is, if you want, the modern view of Yukawa already 1 century ago. That is now at the basis of the Feynman diagram that we will be studying next week. Okay, and at the basis also of the modern quantum field theories. Okay, that are the theory framework for particle physics. Now, this quantity here is then called the bosonic propagator. Okay, it describes the propagation of a boson, okay, from one fermion to the other. So this is the bosonic propagator, and represents, in fact, the probability amplitude for a mediator boson of mass m and momentum q to propagate from one fermion to the other. What about now the two constants, G0 and G? So these we have been introducing before, okay, as let's say the charge of the interacting particle and the intensity of the potential. But now in the Yukawa approach, okay, G0 and G are called vertex factors, okay, and represent the probability amplitude for the emission of the boson at this vertex here, and for the absorption of the boson at this other vertex here. Okay. So let me just read this. So the two constants G0 and G, which are called vertex factors, represent the probability amplitude for the emission and absorption of the mediator at the vertices, and describe the coupling of the extended boson to the scattering and scattering particle. So this is the strength, okay, that couples the scattering fermion with the extended photon, and this is the strength that couples the other fermion to the same boson. Now, let's consider the first part of this diagram. So let's, for the moment, concentrate on this part here, so on the top vertex. Okay. So here we have an interaction of this type here. So initially we have a fermion F, and then at a certain moment the fermion emits this boson, okay, and propagates. So F and E denote the scattered fermion and the emitted boson. Now the problem is that if you only consider this part of the diagram, then this violates energy conservation by some quantity. Okay, so the initial energy is different than the final state energy, and you can see in the following way. Okay, so consider the this emission process in the center of mass system of the fermion. So the initial energy is just the mass of the fermion, which is at rest, and then the final energy is the total energy of the emitted fermion and the total plus the total energy of the emitted boson. Now we can express these in terms of the momentum energy relativistic expression that we know already. And so you see that MF is just here. So we are summing all positive quantities. And so by sure, this quantity here, so the final energy is greater than MF, which is the initial energy. Okay. So there is let's say an energy unbalance. So energy conservation is violated at this level here. And this is also true in the case the boson, the extended boson is massless. Suppose, for instance, this is a photon which has 0 mass, then again emitted by an electron, for instance. So suppose now the process is this one. So now the initial energy is the mass of the electron, which is at rest, and the final energy is the total energy of the electron plus the energy of the photon. Okay, and since it is massless, it is just the momentum. But again, all this quantity is greater than just ME. Okay, so again, energy is not conserved also in this case. Now, in reality, you know that an electron can, of course, emit a photon. Okay, so this is, let's say, kind of real process, but only in the presence of a third body, a third particle, for instance, an atomic nucleus that absorbs the exciting momentum. So only if this process occurs in the vicinity of another particle that can absorb the exciting momentum, then energy momentum will be conserved. Otherwise, this would be energetically impossible. Now, let's now concentrate on the bottom vertex of the diagram I showed before, okay? And of course, the same problem occurs here, okay? So the violation of energy is now opposite in the absorption case. It will be minus delta E. So in this case, we have a boson, okay, that then interact with the fermion and we will start with the propagating fermion. let's make now a comment here. So the net energy violation delta E, however, is allowed to last only for a very short time interval delta T allowed by the uncertainty relation. So you know from quantum mechanics that energy can be violated, but only for very short times, such to fulfill the uncertainty principle. Okay, so we can extract delta T from here, and we see that the delta T, so the time interval where energy can be violated, must be smaller than h bar divided by the energy violation. Okay. Now, in the time delta T, okay, the boson can at maximum reach a distance c delta T. Suppose that the maximum speed, you know, is the speed of light in the vacuum. So the maximum distance, okay, that can be covered by the extended photon in time delta T can be c delta T. Okay, so one can use this to estimate the range of the force. So the range of the force mediated by the extended boson. So the range of the force, the maximum range of the force, can be given by the maximal length traveled by the extended boson. So we now substitute delta T with this expression here, okay? So h divided by delta E, and we want this to be maximum, so we want the energy to be minimum. And the minimum energy is just the rest mass energy, okay? And so we end up with h bar divided by mc, which is exactly the result of Yukawa theory, okay? So the range of your interaction is inversely proportional to the mass of the exchanged boson. Okay, so okay, let me give you some example here. So consider, for instance, the electromagnetic interaction. Okay, we know that, and we will study, of course, that the exchanged boson is the photon. So the photon is the gauge boson of the electromagnetic interaction. We know that the photon is a massless particle, so mass is equal to 0, and as a consequence, the electromagnetic interaction has an infinite range. If you put a charge into the space, okay, this will create an electric field all over the space up to infinite distance, as you know. What about the weak interactions? Now, as we study, the gauge boson, the weak interaction are the W's and the Z, which are now very, very massive, order of 100 gigaelectron volt. And so, if you put now here 100 gigaelectron volt, you will get a very, very small range for the weak interaction, which is in fact of the order of only 10 to the minus 18 meters. So we can actually say that the weak interaction is essentially a point-like interaction. Okay, the range is consistent with 0. Then there is an exception, which are gluons. As we study gluons, which are the mediator of the strong interaction, they are also massless, like the photon, but the strong interaction has not an infinite range, but actually a very small range, 10 to the minus 15 meter, which is the dimension of a proton, for instance. Okay, and so these appear to be inconsistent with what we have seen here, but the reason for this is intrinsic into the theory of strong interaction, okay, the quantum chromodynamics, and this deals with the problem of confinement of colored object, and this will be studied, of course, later on in the course. Okay. Now, since the violation of energy conservation occurs within the uncertainty principle, it is not measurable, it is not observable, and therefore it is allowed, it is possible. So the net effect is the exchange of energy and momentum between the two fermions through the exchanged boson, and this is in fact the exactly way fermions interact. Okay. Now we have to deal with this, let's say, energy violation, okay, concerning the exchanged boson, and a common way to deal with this is to assume that, or to impose that, energy and momentum are conserved at the vertices of interaction. Okay, so let me go back for the moment here. So we impose that energy and momentum are conserved at this point and at this point, okay, but the exchanged boson does not satisfy the energy-momentum relation, okay? So one way to say that there is an energy violation, okay, in the process between the emission and the absorption of the emitted boson is to say that the energy momentum are conserved at the vertices, but the exchanged boson does not satisfy the standard energy momentum relation. Okay. Now, real particles, okay, are those that satisfy this relation, so with an equal here, are called on mass shell, whereas particles that do not satisfy this reaction are called virtual particles, or off mass shell, okay? So essentially the interaction between fermions occurs through the exchange of a virtual boson. And as we'll be studying next week or the week after, this is in fact the basis of the approach of the Feynman diagrams and of the modern quantum field theory, and so essentially of the standard model of particles. Ok, io mi fermo qui oggi. Se ci sono domande potete farle, se no ci vediamo domani alle 11.
No? Ok.
Ok, domani parleremo di la teoria di Dirac, quindi la cominceremo domani e la finiremo con la settimana prossima. Quindi introdurremo realmente al formalismo della meccanica quantistica relativistica. Okay. Se non ci sono questioni, ci vediamo domani alle 11.
Va bene.
Sulle stesse frequenze.
A domani.
Arrivederci.
A domani. Ciao ragazzi.
Grazie, arrivederci.
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 Arrivederci.